Okay, today's lesson is going to cover the Doppler effect. Two objectives: recognize the Doppler effect, and then also determine the direction of a frequency shift when there is relative motion between the source and the observer. Okay, as a quick review or reminder, remember that the only thing that impacts the speed of a wave is the medium in which it travels through. So even though we have our wave speed equation off to the right, any change in frequency only affects the wavelength of the wave. Okay, the speed of the wave stays constant. Okay, we need to keep that in mind as we move forward talking about today's lesson. Intro to the Doppler effect. Here's a clip from the Big Bang Theory that just kind of will give you a very good definition. Plus, it's just fun.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint.
A choo-choo train?
Close.
A brain-damaged choo-choo train?
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Okay, in that video clip, Sheldon gave an accurate description of what the Doppler effect is. But we're going to kind of baby step our way to actually looking at what happens to actually create the Doppler effect. Let's start just with how waves are created with a stationary source. Okay, if you watch that animation, okay, basically what we're getting is a circular wave pattern created as the source in the middle is producing a wave at a constant frequency. The waves have a constant speed in all directions, which is why the wave fronts in every direction are all the same size. Let's start to move the source, and what you're going to notice is a very different wave pattern. We're still creating waves at the exact same frequency as before, but the center of each new wavefront is now slightly displaced to the right. Okay, hopefully you kind of are noticing again that black dot, the source that's creating the wave, is moving to the right. What happens then is we get, okay, those are becoming closer together, and then on this side they're becoming much more spread out. This one's moving even faster. So hopefully the only difference that you're noticing is, again, the wave fronts become much more bunched on the right and much more spread out on the left. Okay, if this was sound, if this was you, okay, the frequency is greater, so the sound would actually be a higher pitch. If you were standing on this side, the frequency is lower, so you would hear a lower pitch sound. What that's called and what we just witnessed happening is what's known as the Doppler effect. The definition of a Doppler effect is just the change in frequency due to the motion of the source or the observer. It's important to note, or it's important to say, that the perceived frequency is what's changing, not the actual frequency. Okay, typically we think of the Doppler effect as it applies to sound, but it actually applies to all different types of waves. Okay, if you look at the diagram to the left, okay, there's two different terms that are associated with the Doppler effect. Okay, the first one is a blue shift. A blue shift just represents kind of this part of the wavefront where the waves are bunched together. What you get on a blue shift is a much higher frequency than what would actually be produced. The wavelengths are smaller, the frequency goes up. The red shift is the part of the pattern where the waves are spread out from each other. Okay, you have longer wavelengths and lower frequency. The red shift, blue shift terminology just comes from red light and blue light. Red light has longer wavelength than blue light. So that's where the terms red shift and blue shift come from. Okay, again, when we're talking about the Doppler effect, all it means is that there's a change in frequency due to the motion of the source or the observer. So that police car, again, it's producing the exact same sound no matter where you're at, but what you hear is what's different. This animation is going to allow us to do is kind of listen to how the Doppler effect changes the sound that we hear. Okay, so right now, we've got the microphone in front of our source. Okay, so you can hear the frequency of the clicks change whether we're in front of it, so the waves are close together, and then how it's going to change behind. If I change the speed of our source to actually be faster, the Doppler effect is just more amplified. So we had lots of fast clicks in the beginning and now lots of slow clicks at the end. Okay, here's what the Doppler effect would sound like in real life. Okay, so here's a fire engine. What I'd like you to do is close your eyes and see if you can tell when the fire engine is coming towards you, once it's past you and is moving away from you. So you could clearly hear what the Doppler effect sounds like. If we make our source go even faster, okay, so now the source is moving at the exact same speed as the wave is able to move. What I want you to notice is the difference in the pattern. Notice how on the right-hand side there's an intense pressure front because all of those waves are overlapping. What we're getting at that pressure front is constructive interference. If this was a sound wave, we wouldn't perceive it as a pitch, but rather just as a loud thump. This is what's known as breaking the sound barrier. Okay, here's kind of a fun fact for you. Jet pilots flying at what's considered Mach 1, or what you're observing on this animation, report that there's a noticeable wall or barrier which they have to penetrate before they get to supersonic speeds. This wall is due to the intense pressure front. And when you fly within that, it's very turbulent and bouncy. Okay, so again, think about it. There's all kinds of constructive interference going on right here. If we're able to move even faster than the wave is able to move, we get a cone-shaped wave pattern behind us. Okay, notice again, the black dots are source, and the new waves are being created actually behind it. Okay, imagine that you're standing right here. Okay, if this was a sound wave and you're watching, let's say, a plane fly overhead, you would actually see the plane before you ever heard anything. You wouldn't actually hear anything until you moved to this position. You wouldn't hear anything until you moved to this position right here. So you actually would have to have the sound wave hit you before you would notice anything. Okay, this particular pattern is what's known as a sonic boom. Okay, the sonic boom is when a supersonic aircraft passes overhead. And again, you see the plane before you ever hear it. The sound is traveling slower, or the wave of the sound is actually traveling slower than the aircraft is moving. And so you get an intense pressure front on the Mach cone. That's what's causing the shock wave. The only way to get kind of that shock wave, again, is if your speed is traveling faster than the speed of sound. Okay, most of us, okay, are experiencing this kind of flight, the subsonic flight, when we fly in our airplanes. Some of the faster planes are actually transonic, and then when you get into the military aircraft, that's where you're getting supersonic, and then theoretically we can also get hypersonic. Okay, this is just kind of a little fun fact. So when we talk about planes, when they say the Mach number, what they're referring to is how quickly the object is able to go relative to how quickly the sound speed is able to go. Okay, here's a quick little recap video to go over some of the different patterns that we've noticed.
We're all used to the idea that light travels faster than sound. Think about thunderstorms. You always see the lightning before you hear the thunder, despite the fact that they both occur at the same time. Sound travels at approximately 330 meters per second, which is pretty fast. However, man has been able to beat this speed and break the sound barrier with supersonic travel. The incredible thing about breaking the sound barrier is that it not only produces an audible effect, but also a visible one. Take a look at this picture. You can actually see the effect on the air as the plane blasts through the sound barrier. Isn't that amazing? The reason why this occurs is because as the plane travels through the air, it pushes the air out of the way, which creates pressure waves that travel at the speed of sound. This is similar to the waves created by the bow and stern of a boat as it moves through the water. As the plane approaches the sound barrier, the air cannot get out of the way quick enough, and it is squashed together into one big shock wave that is travelling at the speed of sound. This shock wave begins at the nose of the plane and ends at the tail in steady flight. It forms a kind of cone shape that surrounds the plane, as can be seen here. The pressure inside the cone is not that much greater than normal air pressure. However, since this overpressure is released very quickly, it is audible as a sonic boom. Have a listen to one. There are actually two booms that are produced, one at the nose and one at the tail, which you can see in this video. However, they usually pass over observers almost at the same time, and so most people will only hear one. It's not just fighter jets that can produce a sonic boom. Perhaps the most famous form of transport that could break the sound barrier was Concorde, which was a commercial airliner before it was put out of use in 2003. Space shuttles can also break the sound barrier, but only when they re-enter the Earth's atmosphere. Well, that's all we have time for, except for this last fact. Humans are actually able to produce a sonic boom using their hands. The crack of a bullwhip is actually a sonic boom. This is because the end of it is travelling faster than the speed of sound. Now that's fun. Well, that's all for today. Until next time, remember, science is fun.
When the source of the wave is actually traveling faster than the wave is able to go, you get that either that bow wave, a two-dimensional shape, or a shock wave, a three-dimensional shape. Okay, so the airplane one is hopefully you saw in the video. The airplane is traveling faster than the speed of sound. If the weather conditions are just right, you actually see that cone wave being produced behind the aircraft. If you've ever been on a boat in water, you're actually familiar with bow waves. We don't really call them bow waves though. Instead, what we call them is the wake of the boat. Okay, so you can kind of see from the picture on the left, those V-shaped forms behind the boat. That's just the fact that the boat is traveling faster than the waves of the water that's being created behind it. Now, the faster that the source is able to go, whether it's the boat or the plane, the more narrow that cone shape is going to be. Okay, here's another quick video on supersonic flight and sonic booms, okay, that has some kind of pretty cool imagery that I want you to see.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools, and as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
Okay, let's get into some of the math associated with these phenomena that we've been watching. The Doppler equation is what's listed below, and let's kind of go through some of the variables. Okay, again, the goal of the Doppler problem is to look at what the perceived frequency is when the source or the observer is moving. Okay, so to kind of start, f of s is the frequency from the source, which is also called the actual frequency. Again, this value is a constant value from the source and one that's not going to change. F of L, the frequency of the listener, that's what the observer is going to notice or pick up. This is your perceived frequency. Notice how we have just plain old V on the top and the bottom. This is the velocity of the wave that's being produced. Typically for sound, it's 340 meters per second. I would write that down. V sub L is the velocity of the listener. Notice how I've got a plus and a minus. The plus and the minus are used whether or not the listener is moving towards you or whether or not the listener is moving away from you. On the bottom, V sub S is whether or not the source is moving away from you or whether the source is moving towards you. Okay, now notice the change in the pluses and the minuses. Towards for the listener is a positive number, but towards for the source is a negative number. Okay, think about this for a minute. If the two objects are moving away from each other, we're going to have a redshift, which means my frequency is going to be lower. If these two objects are moving towards each other or closing the gap, my frequency needs to be higher. So it's all about trying to get the numerator and the denominator to work out so we actually get that higher and lower number to come out for our perceived frequency. Okay, let's try one together. Okay, here's the problem. We have a 50,000 hertz sound wave directed toward an object moving 3.50 meters per second toward the stationary source. What's the perceived frequency if the speed of sound is 340 meters per second? Okay, let's start out and identify what we've got. The 5,000 hertz, that's the frequency of the source. Okay, that's what's being created by the object that's moving. 3.50 meters per second towards, that's the velocity of the listener in this case. The source is stationary. So our V sub S, this is going to make our problem easier. Our V sub S is going to come out to be 0. Okay, using that equation, let's put in the information where it needs to go. So the goal is to find the frequency that the listener hears, okay, when we have the following motion described above. Okay, we've got a 5,000 hertz sound wave. We know the speed of the wave is going to be 340, so we're going to put that on the top and the bottom. Our source is stationary, so it really doesn't matter whether I add the 0 or subtract the 0. The denominator is going to be the same. Okay, now the velocity of the listener is moving towards, which means I need to put a positive sign in the numerator. And then the velocity of the listener goes in there. Working this out, gives us an answer of 5,051 hertz. Okay, that should make sense that we got a value greater than the frequency of the source because the objects are moving towards each other. Okay, how does this problem change? Okay, if the source is moving away. Okay, we're still going to set it up using the same equation. So the frequency of the listener is equal to the frequency of the source times the speed of the wave. I'm going to put that on the top and the bottom. Okay, if the source is moving away, I need a positive sign on the bottom. And let's assume the listener is standing still. Again, it doesn't matter whether I use a plus or minus when I'm dealing with a 0. Typing that in the equation, working it out, okay, gives us an answer of 4,949 hertz. Okay, again, that answer should make sense because if the source is moving away, we're going to get a lower frequency because the distance between them is increasing. Okay, on my big campus, I would like you to try some of these problems on your own. Okay, there's a Doppler homework worksheet, okay, that's got a few problems on there. There's some review just for the wave equation because we haven't done any of those. Those are due next class. Also on the bottom of that worksheet, what I would like you to do is research, okay, some common applications of the Doppler effect. Okay, see my big campus for details. Okay, I'll see you in class next time and we'll answer any lingering questions you have then.